Okay, I think that's actually working now. Yes. So first things first, I need to figure out how to bloody share the bloody thing. Because this is a very professional setup, clearly, and not at all totally bullshit and on the spot. Yeah, so the sort of main problem that I was having here was that the YouTube website where I do the streaming couldn't connect to my webcam software, which is managing literally everything else. Because I could get something like OBS, but I can't be bothered. And I had Logi Capture. Thought that would be enough. It's not. Cool. So, in case someone actually finds this video, or this stream rather, let me go to the other thing. You can see highly professional here. So the thing I'm doing today is trying to design a convincing PCB for a MIDI clock. A MIDI clock that's basically just a microcontroller putting out a signal on MIDI, syncing all the other devices. So you'd be able to say, 120 BPM, and it will just generate a 120 BPM pulse, like boom, 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 over MIDI. I'm planning for some output jacks. So this is our first version of this that I have, which is Arduino based. I actually do have it, right? It's let me get to my incredibly professional setup. It's this thing, right? So I do actually have a version of this already. It's got an Arduino in the back, some bodge capacitors, that kind of thing. I can power it on if I can find the right USB lead. Right, so yeah, it has this little bit here. The encoder, you can twist it, and it'll go faster. It'll go slower. Now I've realized that I made a mistake, because when I push the encoder button in, it should stop and start the clock. It doesn't do that because I wired that wrong. And I also realized that I wanted to put some new features on it as well. I'm kind of doubtful about being able to do on an Arduino. So taking this design, and it would help if I have video. I'm taking this design and I'm going to re-implement it using an STM F103 microcontroller. The STM F103, why? Because STM32 F103, right? It's in JLC PCB, it's a basic part for SMT assembly. So you only pay for the microcontroller. like there's still some charges, right? But it's basically you can pay someone else to solder it for you, which is great. And it also has native USB, whereas the Arduino obviously doesn't. It has to go through a USB to serial adapter, unless it's a what is it, Leonardo? But I haven't seen sort of that particular Atmel chip in a nano form factor. I'm pretty sure you could do it, but it's not as popular as the clones of the original Arduino Nano with the Atmel non-USB chip. So the plan here, right, is also I wanted to try something else. So I've got this microcontroller here. It's got USB coming in, and it's got all the support circuitry. I'm also opting to go for a Type C socket, Type C connector on it. Not because I hate myself and I want to suffer while I solder it up. No, you can actually get USB Type-C sockets which only expose USB 2.0 pins and a few other bits that are required to make it work, which is great because that's literally all I need it for. Because this can only do USB 2.0 full speed, 12 megabits a second. Now, what that means is it can be field updatable, right? Field upgradable, without having to use the SWD connector. Just plug it in through USB. I guess there's a program to run which will update it, put it into like bootloader mode or something. I still haven't figured it out. And yeah, that basically means that I can publish firmware updates and people can install firmware updates without having to download the Arduino IDE. Which I suppose you could do it other ways as well, but and the other thing is I can actually make use of this this USB line in my firmware. So I can, if I wanted to, I can turn it into a MIDI out or a MIDI in or something like that. I could possibly reprogram it for other uses. So yeah, as far as all the other features, so there's the encoder here, right? So you twist it one way, the BPM goes up. You twist it the other way, BPM goes down. You can press in the knob, and it'll start and stop the clock. The other thing it has is it's going to have 4 configurable outputs. So these would be Eurorack compatible, or at least 0 to 5 volt logic level, which it'll just be a square wave. And I've set it up such that you could actually toggle between different speeds. So you can set it up all of them to have like the clock. So a rising edge every half a second. Yeah, half a second for 120 BPM. Or you'd be able to double it or halve it, that kind of thing. And some LEDs to let you know what the hell's going on. It's also going to have a display like this one, right? But I think I'm going to opt for the so this one has the 128 by 32 display. I think I'm going to go for the taller display, the 64 pixel one. same drivers, just a bigger display, and use the other line of text to also display the clock multiplier applied to these outputs. The sort of reason I do that is I can have these outputs divide and multiply however I want, because the MIDI clocks, the MIDI clock needs to run at like 24ths or something like that. It is quite high speed compared to the actual BPM. And also, I found that you can't really skip stuff, so timing is kind of critical. In fact, I've in the Arduino version, you pretty much can't do it without a timer, like without using a hardware timer through the registers, through the Atmel, like through lower layer. So you have to take direct control over the timers, because there's like no library that lets you do it, which is interesting. At some point you realize that the Arduino ecosystem is just a nice wrapper around kind of a shitty microcontroller. Well, there goes my there would go my monetization if I had any. So I'm just trying to check if the picture's okay. No, it's not. Doesn't matter. Nobody's watching the stream anyway. Well, 3 people are watching the stream, allegedly. Well, one of them's me, because I'm monitoring it on another computer. If you are actually watching, say hi in the chat. And if you're not a bot or something, yeah, I have the chat open on another screen, so I can answer questions and stuff. Again, still don't really know what I want to do with these streams, if I even want to keep them going. So let's go with PCB new here. So I've got this microcontroller set up here. I've also got it in this CubeMX. So that actually gives me the pinout, right? So I can see what the real pinout of this is going to be versus the schematic symbol in KiCad. And I can configure the peripherals. So here I've got timer 4 is set up for encoder mode. And that means that I'm going to be using one of these timers to actually read the encoder. So I think with Arduino, I don't know what the encoder library is doing. It's probably just counting pulses on an interrupt, which, great. With STM32, you can actually put one of these timers to work, to actually act as a quadrature decoder. So it takes in the quadrature modulated signal from twisting the encoder, right? You twist it, it'll generate a couple of square waves which are offset, and like that tells you which direction and how fast the rotation is going. So you can actually put one of these timers to work on that, and presumably DMA the value into some variable in memory, and not have to bother with actually wasting clock cycles on keeping track of the encoder, because the timer will do that for you. And then obviously I've got other timers as well. Channels and stuff doesn't really matter. Combine channels, yeah. Yeah, so the STM32 has a lot of funky timers, and I'm pretty sure I'm going to be using at least one of them to drive the MIDI signal, and possibly like either use one of them for everything, have like a time-based clock, and then subdivide that later in software. Or I can possibly set up, because I have 3 other timers, right, to play with. I can actually set up one as MIDI, and then 2 of them could potentially take care of the square wave signal. Although I'm not super sure if I like that idea, because I want the Eurorack level clocks to be fairly tight with the MIDI clock. So I've got the MIDI here on these on this USART. So MIDI is just serial. It's serial over a blinking LED, which is why this you've got this sort of funky thing here. So I'm basically the MIDI cable, right? It's blinking an LED over a long wire. So you're basically blinking LED in the other device, in the MIDI. I want to say client, but it's not really client. Receiver. So it's basically going into an optocoupler, and the idea here is that you can actually galvanically isolate the sender and the receiver, so that if the sender crashes and puts out, I don't know, 20 volts onto that LED, it doesn't necessarily completely blow up, because to be standard compliant, you're supposed to have protection circuitry around that. And as a sender, you're also supposed to limit the current from your side. I'm just doing it with that resistor. And the other thing is that this LED blinking is going to be the inverted UART, because on the other side it'll get inverted again, and it'll just be UART again, and you'd be able to listen to it on serial, and it's like it has some baud rate, like a specific MIDI baud rate. This is MIDI 1.0, by the way. This is completely, just that. No MIDI 2 going on here, nothing like that. So yeah, that's the sort of design, sort of functional design for this. And here, yeah, 3.3 regulator. Back here, I've actually got a buffer to take the 3.3 volt signal from the microcontroller and turn it into Eurorack level signal, and also to drive the LEDs, because the LEDs will be driven from the same signal. And it basically just means that I don't have to use so many pins. Although I do have a lot of pins free, but if I can get away with getting 2 LEDs blinking from the same signal, that's great. So I've talked about the theory of operation here. Let's design the PCB. So I'm going to pull the schematic, pull the net list and everything. And it's clearly doing something. There we go. So yeah, I think the other, yeah, there's like one problem here, which is this thing doesn't have the same, these jacks don't have the same sort of pinout. So it's going to complain that it doesn't have the same pinout, but whatever. Right, let's do that. So obviously, KiCad thinks that we can get away with having this footprint, but that's bollocks. As it stands, even the sort of miniature version is going to be quite big. So what I like to do first is figure out how I want the inputs and outputs to look like. So what I was kind of thinking, right, is I would take these audio jacks, these Eurorack 3.5 millimeter jacks, and arrange them sort of 1 centimeter apart. So I'm using 0.1 millimeter grid here, which means like at this zoom level means that these two dots are 1 centimeter apart. Right, so let's grab this guy. Just aligning it. And this guy. And this guy. I think that's how I want it to look like. Let's see. Let's view this board layout here. Yeah, so it's going to be something like that. And I can probably check. Yeah, this is sort of 10 millimeters or one centimeter apart. This should be enough for a lot of Eurorack type cables. It might not be like there are some cables which are kind of chunky at the end, but that shouldn't be like. I think most Eurorack patch cables aren't. So I've got these LEDs here, which they go somewhere in here, I believe. Expect them to be blue because, of course, it's supposed to be a futuristic product, and so blue LEDs it is. The display I'll also get blue. Could do white, but I think I'm going to go for blue, like on this one. It is a nice blue color. So how it works is I need to set it up quite close to yeah, let's do here. And this one into here. Cool thing with KiCad is that you can actually use the keyboard to move stuff around. So you can kind of position things roughly with the mouse, and then use keyboard to move in sort of 0.1 millimeter or 1 millimeter increments. It is 0.1 millimeter here. And that basically lets you dial positions in based on whatever grid system you've used. I think that's quite a nice feature of KiCad. It's probably in all the other EDA packages except for Easy EDA. Maybe it's even in Easy EDA, but Easy EDA is such a weird piece of software. let's see. These are 1K resistors and they're quite big, so they're probably the LED resistors then. Right. Do I want to lay it out like this? Yes, because nobody's going to look at it. I mean, you're looking at it. That's true. Okay, and you here. Great. So these are driven by this buffer chip. All right, and the sort of inputs and outputs for this are a little all over the place. So you can see that I'm rotating this and it kind of just goes bananas. Yeah. I think I'm actually going to have to do this, which is kind of stupid because it means I'm going to have the input signals. I can make them come up from the top, but yeah, the sort of signals are, the actual driving signals are going to be weird. I think that's the least bad version of this that I can come up with. Right. So that's the buffer chip here. But so I'm not sure where I want this buffer chip. I can either have it quite close to these outputs, or I can have it sort of below the screen. So I am actually going to use one of the modules like this with the OLED screen, and that basically means I get some sort of routing space. Not a lot of clearance, but there's some space I can tuck chips under. It's not going to be like directly soldered to the PCB. All right, now let's see. Might have to space these out actually because they are kind of tightly packed. So let's see. If I leave a centimeter between them, that just makes it huge. But maybe that's a good thing because I'm going to have buttons over top of it, and I don't want it to be too cramped. I own some Korg Volcas, and they're pretty interesting machines, but they're not particularly ergonomic. So let's make sure that these line up. Cool. So now I've got these lined up correctly. So there is actually now a centimeter of space between them, which that should actually be a lot of space. So all the cables will fit in. So just trying to dial this this buffer chip in. I think I will have it here because this is sort of part of the 5 volt 5-volt part of this design. All right, so now I've got this guy. So there's the one sort of thing that I need to pay attention to here if USB pins are, because they're a sort of fiddliest thing to. Well, I say that it's probably fine because it's only like 12 megabits, and off that I probably only need 1 megabit a second for any sort of anything that isn't firmware updates. Even then, the firmware is going to be really small. But I still like to do this properly. So I can either have the USB coming in from the top or from the right. I think I'm gonna have it come in from the top. Right. Great. So something like this. I've got this. I've got the USB here, and now I also need to put the display somewhere. So where do I want the display? Well, interesting. So the other thing I need, right, is I need space here for buttons. So actually, let's pause this for a second and let's get the buttons in. Buttons and their respective debouncing capacitors. Because you shouldn't, bouncing buttons aren't the greatest thing ever. So let's put it down here. Put this one down here. Number 4. There's actually some integration between eSchema and PCB-new. So between the schematic capture program and the PCB layout program. Oh, it screwed up my grid for some reason. Did it? There we go. And I think that's also dialed in. Yeah, good. So capacitors. I'm telling you, in sort of digital designs, I think you'll end up placing a lot of capacitors, and in analog designs, you end up placing a lot of resistors and capacitors. So this is probably not the greatest thing to do, but I'm gonna try and tuck this capacitor between the pins of the button. It's probably not gonna work, but whatever. Okay. Next capacitor. Chat's quiet. It's just me right now. Next capacitor. That's going to be the last one for these buttons. And I also like to resize the reference labels of some of the smaller components, because it kind of tickles me that for 0402 components, the reference label is frequently bigger than the component itself. It's funny. It just is. Great. So now I can think about putting this buffer chip back in, because now I know more or less what sort of space am I dealing with here. All right, so let's do that. And then let's figure out where the MIDI connector is going to be, I think. So I think I want to have this on the right. So like if you look at this one has the output to the right as you're looking at it, right? And that just means you'll be able to put in sort of leftmost bit of your setup, or maybe like clip it to your sequencer or MIDI keyboard if it takes in sync, that kind of thing. Right. So I think that's what I'm going to do here. The MIDI socket, the DIN5 socket, is definitely the biggest component in this whole design. I think that'll do. Now, the other thing is going to be the actual encoder itself. So I'm kind of putting this buffer chip here. It really doesn't need to be here. What does need to be here is the encoder, because that's actually important. So I'm trying to line it up such that it lines up with the center of the MIDI of the DIN pin, right? There we go, and also the center line of the board, or what will be the center line of the board. So I've got that. Next up, I'm gonna need this. Is that equidistant? I believe maybe. I still need to make sure that this has the right dimensions. In fact, let me pull up. Yeah. Adafruit. Because all of those displays are basically just this Adafruit breakout clones. This code is discontinued. Well, okay, maybe it's not. So it's probably like one of these modules, except this is yeah, because I've had I was looking for how to get these modules without the carrier board, so that's kind of useless. I want OLED mechanical. Right, I'm basically just looking for the dimensions of this board, just the dimensions. Outline drawing. Well, I believe that might be what I'm looking for, but it's an AutoCAD drawing. Helpful, very helpful. Let's see, what can open this file? Let's try. Let's try the GNU image manipulation program. Because it, ostensibly that's an image. Doesn't like that. Let's try LibreOffice Draw, maybe? Because, it sometimes opens some bizarre formats. Yeah, cheers. It's not a Word file. Ah, there we go. That's much better, actually. So yes, I've got this overall sort of schematic for like any sort of holes and things. Yeah, good. Which means what I can do is just right, so it's kind of there, which is on top of this line. Let me go to front silk screen layer to basically put myself a reminder of where this bloody thing is supposed to start and end. Right, so so let's do that. Let's press enter. Right. And I'm basically not doing anything particularly exciting right now, because most of the magic is happening in the actual status bar. And I can't even show you this without losing the position of the line. So that needs to be another 27-ish. 27.3, sure. Basically just need a sort of broad outline of how big this display is going to be. Great, so about yay big, which means I've got to move it so that it doesn't interfere with the encoder. So I've got this, I've got this, and then let's just move it here. That looks safe. And obviously, the other thing I can do is I can rotate it. So that the pins are here, and then in the other, at the top of the board, I can actually put all my USB related stuff. Right, I think this is reasonable. So the sort of user interface sketch here is going to be, you've got these buttons here, you've got the screen, you've got an encoder, which is also a button, and then you've got your outputs, and then the USB input. Which I'm going to poke out slightly. Yeah, I need to make sure that this is not covered by the display, because yeah, under the display, that's pretty much only space for chips and small things, not a connector, even a USB Type-C. So I believe this means I've got my board outline pretty much set up. So let's do that. Let's lock in this board outline. And I'm pretty sure that's going to be a reasonably big board. Yeah, it's going to be like 120 by 120, I believe. Well, I can measure it. Add dimensions, right. This actually needs to go up because I want the audio jacks to be poking out. There we go. That goes in here, and that goes into here. And from there on in, if I do 3D viewer, I know there's a, interesting. I know there's a shortcut for the 3D viewer. I'm not using it because it's also a shortcut in Logic Capture, and it could possibly do some weird stuff. Oh, that's brilliant. I put it in Eco 2 user instead of edge cuts. That's why. Okay. Can I put you on a different layer? I can. Edge cuts, please. Because they're the same color, you see. So the board outline or edge cuts layer is the same color in the layer color manager thing as this Eco 2 user, which is great design. Let's save it, and there we go. Now, and I actually did it. But I guess Alt 3 is just the same view as I was already using. So it did absolutely nothing. Great. So yeah, there aren't very many 3D models loaded. And also this is probably going to be pins rather than pin sockets. But yeah, it's got stuff. Right. Let's add some of these dimensions in, because while I'm here, I might as well. but not on edge cuts because that's psychotic. I think it lets me do that because edge cuts is a graphics layer as opposed to a routing layer. So it thinks that, oh yeah, edge cuts, the thing, and the dimensions, that's also a graphics thing. Therefore, you can put dimension markers on your edge cuts layer. That's brilliant. So it's an 8x8 centimeter board. I think they'll make it. Yeah, I'll basically make it this size, only slightly more square. Rectangular. You know what I mean. So these are all the sort of user-facing components. Let's pull this slightly further up. Great. So now I can actually put stuff where it needs to be. So I'm going to put this buffer kind of to the side here, really, because that's at this point, that's the only space. It's the only logical space I have for it. The microcontroller will go under the display because that's always fun. Right. And I need to rotate it such that, yeah, the USB pins are facing the USB socket. Right, great. Next thing is crystal. Right. So the crystal is also going to be kind of tall. So ideally, I want to have it not under the display, which I guess means I'm not going to put the microcontroller under the display. I'm going to put it somewhere here. Yeah, let's put it somewhere here. The next part is figuring out where I want to put the crystal. And let's say I want to put it somewhere here. And then I've got the crystal, the other crystal components to worry about. So I've got this resistorb. Now again, you can see here that this is a no thank you. I want this one. This is a 0402 component, which you know, if you're designing this to solder yourself, you wouldn't be using 0402 components, but because you're basically renting the machine from JLC, like you're renting machine time, pick and place machine time from JLC, you can just go to town and put like super small things in your designs. It's great. I'm not sponsored by JLC, by the way. Kind of wish, but it is just a very useful service, and there are other companies that offer this. I think Seed Studio offers something similar. The problem there is they don't necessarily offer you the JLC PCB parts library. Like there's no integration with a parts supplier like there is between JLC PCB and LCSC. So you basically have to specify where you want to order your components from, and then pay an administrative fee for someone to actually order them online and put them into the pick and place machine. At least I think that's how it works. Right, so this is the other load capacitor for this crystal, and I'm not actually sure if this is the correct value for this crystal, but I can revise that in, because I'm not going to be ordering this quite yet. Right, so that's the crystal situation sorted. Let's figure out these pin decoupling caps. Right, so these guys kind of need to sit next to the power pins of the MCU. And I'm actually going to immediately connect them because yeah, it's just kind of this. And you know, you should have planes and things, but I'm gonna do my ground pores and voltage pores later. I'm gonna actually shoot for this being a 2-layer board if I can get away with it, because that just means cheap. And if I can make this cheap, I can sell it for cheap, and that means people, you know, more people might be inclined to buy it if it doesn't cost like $300. Like some of the other MIDI clock generators out on the market. Like, I can understand if this is test gear, you know, if you need to precisely generate flipping 300 megahertz clocks, but this is MIDI. It's just in, like, you know, it's 32 kilohertz. Okay. Next up, another capacitor. Yes, why not? Let's connect this up. I'm kind of trying to do this like mostly by the book, in terms of decoupling each VCC pin. I'm not using any analog peripherals on this project, so the VDDA, I'm just going to decouple with the same 100 nanofarad capacitor. It's fine, presumably. It just means it won't have the same sort of stability, you know, you might need if you're using this for some particularly intensive, that's in a slightly awkward position. Yeah, you only really need to worry about decoupling VDDA properly with like a LC filter or whatever, if you're actually using the ADCs in a demanding setting. So if you're implementing a low bandwidth oscilloscope, for instance, and you want it good. So let's see, and the last one, I believe that's going to be, come on. Oh, I forgot about this label. So get this label, move it here, and then this guy I'll do the label first so I don't forget later. Right, and I believe this one can just chill somewhere here, because I believe it's for the VBAT pin. Yeah. Not sure if you can see it with between the video compression and downscaling. It's VBAT, which is the sort of watch battery backup. which is an option on STM32 microcontrollers, but I'm not aware of like hobbyist projects that actually use it. Right, so that's the capacitors. There's a per pin capacitors connected and crystal connected. Now I've got this package level decoupling capacitor, which that just kind of sits at the package level. I don't want to say it can be anywhere, but it kind of can. Just has to be close to the package. And I feel this is as good a place as any. I really need to figure out how to make these streams not a disaster like it was today. Because, yeah, there's some weirdness with the software. All right, so that's this bit. So the other thing I kind of want to know is, this is the parts library, right? I need to figure out how sort of impedance matched things work here. Controlled impedance, PCB layer stack up. So I think if I want controlled impedance, I have to go for 4-layer. Yeah. Okay, fine. I'm doing a 4-layer board. Right. There's some rule of thumb, probably. Nominally 90 ohms for the signal pair. Okay, fine. So let's go 90 ohms differential 4 mil space. Great. So if I'm gonna do a 4-layer board, I might as well just configure it for a 4-layer board now. 4 layers, parts on front, please. Actually, I'm gonna go 4 layers, parts in front and back, just for the extra flexibility. I might put some hand solderable parts on the other side. So I've got this, there's a differential pair set up in here somewhere. It might even be back in here. That classes, yeah, differential pairs. Good. So width, I'm going to go for 6.89 mil. Gap is going to be as specified, 4 mil. Ooh, interesting. No, 6.89 mil. clearly not. So 0 to 5 millimeters. Default, yeah, the default track width is kind of weird. So let's say 6 point. Minimum track width. Where is it then? Okay. Back to 0.22 25 millimeters. Let's just say this. And it works. Good. So let's route our differential pair, shall we? Kind of goes like this. Routes both of them at the same time. And I'm routing this first because that's kind of the most important signal on this whole thing. Yes. Good. And you might have noticed that there are two sort of sets of pads, and that's just a USB Type-C thing. So I'm gonna short these together and see if that actually does anything funky. But yeah, that's a sort of USB 2.0 fallback, and I just need to specify some extra thingies. Extra thingies. Yes, I need to add some resistors here to tell, like, if it's connected with a USB Type-C to USB Type-C cable, right? It needs those resistors to tell the other device that now it's just a USB 2.0 connection. And by the way, like, these pins aren't actually that bad. It's because you can solder this type of chip by hand relatively easily, and I think the particular part I selected for my socket is also reasonably easy. Like, you don't have to do any weird stuff to get to those pins. There are some which actually shield those pins here, which means you can't solder them by hand. You either have to use hot air and pray, or a reflow oven and pray. So that's that. Let's see, what is the other thing that is needed here? Oh yes, the 1.5K pull-up resistor that to the 3.3 volt rail plus 3.3 volt, which goes on the USB plus line. And that'll actually go through a MOSFET. And it'll actually go through a MOSFET because I want to be able to reset the USB connection with this USB enable signal. All right, so I can kind of route it like this. There we go, and that's the USB enable signal. That'll either activate this this pull up or not, and you know it'll have its own on-state resistance, but it's like milliohms. Okay, next up, what else to lay out well. I think the next bit is going to be those resistors for the USB cable, because I would like them to be, ideally I would like them to be next to the actual USB socket. So I can put one here. Right. So that's the one here. And then R2 there. And I'm not trying to lay this out super aesthetically, but it kind of helps, really. Great. So now this can go here, this can go here. And then these, these are grounds, and there's also power signal, I think, on B4 and B9. Which has to go through a small bead, right? So that'll go through a ferrite bead into a 3.3 volt regulator. And the reason I'm doing it through a bead is it's just good practice. Yeah, I can say this size. Don't really care. What I do care about is it not having too much overlap with the labels. With the component references. Right, so that's this bead here. Let's go to this capacitor. And that'll form the 5 volt supply. So I think I can actually take a half a millimeter truck. And just make it super weird. Yeah, great job. How are you going to get ground in there? Well, you say that. Can I get away with this tiddler? I can. Good. I understand this is probably not the best design for this, but it's a design for this. And again, it should be reasonably cheap to produce. So even if I screw this up, I won't be too far out of pocket. Right, next one. So that's the input capacitor for the LDO. So seeing how the 3.3 volt section is kind of self-contained here, I'll just plop it down like here, I believe. Yeah, why not? Plop it. Ploppage is happening. I think there is like a default setting somewhere in KiCad to let you set the text size. The problem is I actually like having the bigger field references for bigger components, because to me that just kind of makes sense. and then the output capacitor for the 3.3 volt supply. Eyeballing the correct distance. You understand, there isn't, like, it's not about the correct distance, it's about, it is about aesthetics ultimately, because yeah, when you're doing electronics as for fun, it has to be pleasing to you. How does it look like? Not bad at all. Okay, let's select this track here, track type. Right, and then, yeah, basically now I have some bits to do. So let's first designate a keep out zone for, and this is probably overkill, really. But I kind of want to get a keep out zone for voltage pores under the crystal. I think it's one of them good practice things. Like I believe there are some electronics people on YouTube who would actually give the crystal its own ground pore. Maybe I should be doing that. I might actually revisit this at some point if I feel like I need to do something like this. Right, so that's this keep out here. Actually, basically, I just need to keep out copper pores on the inner copper layer, inner one. The reason for that is I don't want the power plane under the crystal. I just want the ground planes. So now I'm going to add a filled zone, which is going to be the extent of the 3.3 volt plane here. Mm-hmm. And yeah, I want it to be something like this. Okay. And now I can actually break out the 3.3 volt. Let's give it slightly bigger vias. Yeah, again, this is one of those supposedly good practice things. So 1 millimeter via in general with a drill size of 0.8 millimeters. I believe that's kind of, you know, I know JLC can probably go smaller, but yeah, it's one of those things where you're supposed to have big vias for power things and have lots of them. Something about inductance, which I don't really understand, but it's just a thing that you're supposed to do, and I might as well do it. So I think now it has given me 3.3 volts under all of this. Good. The next part of the operation is going to be hooking up the rest of this business. So I've got the setup resistor. So I've got to pull up for the reset line, which I can put anywhere, which means I'm putting it well out of the way for everything, and reasonably in the vicinity of the reset pin. Might as well put it here. I'm not changing the size of this, so that if the user wants to, for some reason, replace it, they can. And it's also not really bothering anything. And there's this boot 0 resistor, which similarly needs to go somewhere where it's out of the way, not really bothering anyone. And that one just goes to ground. Fine. You can go here. It is a big board. I've got, by the necessity of having this connector layout, I do actually have quite a bit of space to play with, which is great. I mean, it's great from the point of view that I can just kind of be lazy, but it's not really great from the point of view that it's an 8 by 8 centimeter board, which at 4 layers, that's not going to be $5. That's going to be like $10. So next up, programming header, which needs to go somewhere where there's 3.3 volts. I can put it. I'm going to extend this 3.3 volt pour right up until the edges of the board, and put the programming header somewhere here. And that's only going to be necessary for like initial programming, I think. I can put it here, why not? Because then the rest I can just do with USB. Which is brilliant! All right, next up, I believe, is going to be the circuit for driving the MIDI output, which consists of a MOSFET and a resistor. Note that I haven't actually put any sort of pull down or pull up resistors on the gates of my MOSFETs or resistors to limit gate current. I believe that the sort of capabilities of the microcontroller itself will be fine, because you can specify pull up or pull down resistors, and it also will probably have some sort of current limiting on the GPIOs. Like that's just my thing. I might do the gate ones, but not the pull up or pull down ones, because those are done through the those can be done in the chip itself. And that just saves me, it's probably not required in this design because it's chunky, but if you have a really small design, that might be helpful. It also, saves me having to specify it, define it, that kind of thing. Okay, so what else am I going to do here? Right, I'm going to specify this at priority level 10, because I also want to put a general sort of ground pour on this layer for 5 volt, so that everything else has 5 volt if possible at priority level 0, which means that I can just be lazy and put this on the entire thing, and it'll figure out where the 5 volt is not needed. So yeah, just do that. And I'm also going to duplicate it a couple times. So you go here and be a ground. You go here and be a ground. And you go here and be a ground. So now I have ground pores. Yay. For some reason, they are slightly offset, which I will not be having that because I'm pedantic. There we go. So yeah, if I refill the zones and check the zones now, you can see that only the 3.3 volt zone is filled because only the 3.3 volt zone actually has any kind of connections. The 5 volt zone, not so much. We can fix this. We should fix this. Yeah, I've got my power sort of traces selected, so let me just break out some 5 volt into vias, like so, get this crow's foot pattern in. And if I refill that, yeah, there's the 5 volt zone and there's the 3.3 volt zone. Should I be doing these split planes? I don't know. Maybe. Probably not. But nobody else seems to be watching this to comment on my progress. So I'll just do that and then be sad when it doesn't work. Great. What else? I've got some capacitors here. What are these? These, I believe, yes, these must be for the encoder. So yeah, the encoder is wired up so that it connects to ground, and it'll be pulled up from the MCU. So let's get this capacitor then. Okay, and let's get the capacitor for the switch, which is here at the bottom. And I can also be cheeky and just put it between those pins. I'm not going to do that. Not here. I'm going to put it here. I've put these guys here, but I'm not sure if that's a good idea. It's probably a good idea for more compact designs, actually, because it's definitely well within the capabilities of the board house to manufacture this. The question is whether this is a good idea in terms of soldering up the buttons yourself later, right? Because they don't do buttons. Like if you go to, I believe if I go to the parts library, they shouldn't be doing buttons. They are doing buttons. Interesting. The buttons are extended parts, but they are here. Interesting. So I can actually get them to do the buttons. I might consider that, Let's look at the data sheet for this. Yeah, it's connected exactly how I would expect it to be. It's a 6x6 button, 6x6 millimeter. Cool, let's do that. Let's specify it in EE schema. Let's actually go to the spreadsheet editor thingy. Where is it? Tools, edit symbol fields. So yes, switch push. All right, great. Supplier, LCSC, supplier SKU. It's that one. Good, good. I'm going to refresh just so that it has all the fields. So, okay, I guess they do buttons now. I don't think they used to do them when I tried this before for assembling this thing, right? But that's kind of beside the point now. And that's all the actual components. So now, it's going to look a little like this. Right, with the MIDI output here and the clock outputs here. Great. So now I just need to route everything. Yeah. Cool. Let's start with routing, doing the shortest traces first. And then the rule is the most important signals first. But if I can connect some of these guys up. Reasonably quickly, that's also great. Right, so I think this clock one signal, that'll just have to go out through like here. Clock to LED, like so. And where's clock to signal? Yeah, kind of has to also do something really bizarre. Because all the signals are on the top. I'm trying to do this without having to put vias in. Because, you know, personal challenge, I guess. I mean, this will have to be like via'd to hell. Like now I have to put them in, but the less things jump up and down, like the more readable the layout will be. That kind of thing. Of course, on the flip side, if you do decide to use vias, you can. There are some bits you can do with them. Okay. So that's the fourth clock channel, and now third, and now I need to do the fourth. So where does this need to go? Here. All right. Let's see, can I squeeze? Yeah, I can squeeze through here. Good. Okay, so that's the front end of this connected up, these clock signals to the buffer. Next, I should connect the MIDI output, and that'll connect to the microcontroller. And I have this mode enabled in KiCad where it literally will shove stuff around when you're routing to make it slightly easier for you to do it. It's useful. It is kind of useful. Okay, that needs 5 volts, right? So just wire that in. That's the other thing. When you're doing multi-layer board designs, you kind of want to preserve your. Actually, I should do this with the beefy setup. You kind of want to wire down for power into your power planes, I guess, but that means I guess your signal space is slightly more limited. I might be talking bollocks. I'm not a professional PCB designer. I'm just doing this because I want a MIDI clock, and I want a cool MIDI clock that drives both Eurorack level gear and MIDI, and has options. Right, next up. So that's connected here. I2C perhaps. That would be a good one to connect. And it could actually be connected from below. Why not? Let's do that. Yeah, because it kind of needs to cross over. Now this probably means I need to do something funky with the 3.3 volt supply to the chip, but that's about it for the screen. Okay, good. Now then, let's why is this showing? Oh, so these need to be connected to ground. They not just tied together, but tied to ground. Yeah. There we go. Right, sync with that, and yeah, now they're actually showing up as grounds because they need to be pulled low to enable the buffer. You see. All right. Let's do some of these internal connections. And clock number 4. Okay, this chip is it's basically 2 sets of 4 buffers, but I've got them tied together so that one does the clock signal on the TRS jacks, and the other goes to the LEDs. Now they should be connected to the microcontroller. And yeah, I can just shove these tracks around. It's fine. The next thing is going to be connecting the switches, but then yeah, that's where the shove feature in Kika is going to come in handy. Because yeah, as it is now, there isn't a lot of routing room here, but there will be. There will be. Same with the encoder. Okay, so yeah, now the switches remain and the encoder. Let's do the switches first. I think I'm going to put that on the bottom layer. So route these on the bottom. And then pop up when I need to cross the I2C lines. At least for this one. For the other ones, I think what I'll do is yeah, use this shove method and go around the display, right? And go from this side. Did that connect? Let's make sure that it does. All right. Next up, clock number 3. Same deal. Run it down here. And then put a via in somewhere here. You can actually put a via right here on this track here. Because KiCad will complain if I don't connect both pads on the if I don't come on the pads on the button, it'll think that it's a net that's unconnected. Yeah, it's probably a good thing. So let's go here and pop out the other side. All right, next up, the encoder. So let's start with the encoder, like the actual encoder signal. So that can go as far as here, and then it'll drop down to the other layer and then come out where it's needed. Same with this guy. I think. Come on, drop a wire. Why did it take? Okay. Yeah, if it has to shove a lot of things out of the way, it can get kind of slow. Also, this isn't a brilliant place to move this. So let's actually just continue up through to here and then drop the via here. Then re-emerge on the other side and into the pin. All right. And then the encoder switch. Which I think I'm going to route through sort of the same general approach. So it'll go here. Right. Under the MCU and then into the pin. Okay, so now the only thing that's left really is well, two things that are left. First, connecting all the MCU signals for programming and things, and then second is going to be making sure that all the planes have connectivity, and then is going to be more or less ready. So let's start with the debug signals, with the programming signals. So let's start with, oh, I don't know, SWD clock. And this is going to be a pin header, but it's going to be like a tiny pin header. Okay, this guy, let's see if, yeah, I can route it past the pin on the corner. And then go into this pin here. And SWDIO. I can drop a via down and route it on the other side of the board. Now reset to go through. Yeah, that's definitely going to have to start on the other side. So yeah, it can go through here, I believe. Pop via, put it in, but the other place it has to go is obviously the pull-up resistor for the reset. And it's in. And then finally, the final signal that needs to be broken out is this boot 0 signal. Oh no. Okay, it figured out what I wanted to do. Yeah, the only issue with this shove feature of KiCad is that it can be quite expensive computationally, or in other words, slow and slightly scarily crash-like when it's trying to solve for moving the pins in specific ways. Okay, so now I believe that's all the actual signals connected. And now I just need to do the grounds. So here, I can consult, well, the grounds and the power, right? So I can consult the map of things And by by consulting the map of things, I mean turn on all the pores so that I can figure out what the hell I'm actually trying to do here. Right, so let's switch to my power setup. Right, and I think I'll because yeah, some of these ground definitely can't access from the top. Some of these you should be able to, though. Okay, that's that one. Right, what else? This needs 3.3. This can have 3.3. So there's, I believe, yeah, all of the planes are connected under our under the MCU. The clusters, the crystal stuff, I believe this guy needs better access to ground, or, you know, access to ground. And then I think this guy might need to be grounded through a via. Or possibly not. What's going on here? It's basically telling me that this copper island is disconnected from other places where with ground. So this is actually, so this isn't necessary. But what I could do is I could drop down a via size and put in some stitching, via stitching somewhere here. So let's do that. Yeah, just a bit of via stitching. Why not? Let's take this off temporarily and then see if there's anything else unconnected. Can't figure it out by just blinking, so let's list unconnected. And these are just the shields for various pins. Good. Design rules check. Track too close to pad. Yeah. So it is probably something that I'll need to end up fixing, but for now, it is a mostly laid out board, which is great. So yeah, you'll have your MIDI output here, you'll have the screen here, you have the encoder here, switches, outputs, that kind of jazz. I think the other thing I might do is actually put the output stuff on the bottom layer so that the user interface, like the top layer user interface stuff, is closer to the top bezel, because otherwise, you might need a long knob for the or long shaft for the encoder. You won't be able to see the screen so much because have you seen the height of this DIN connector? It's big. Okay, I believe that's everything. Unless the stream was flipping crashed this whole time. But I don't think it was. It is attempting to stream in HD. I probably don't have good enough connection for a 4K stream. Nothing in the chat so far. Yeah, cool. So that's actually quite a, it's an all right test case for any sort of streaming setup that I might do later. And also it's got there's a design look. I can design this. I can either try to use it as a base of a mechanical design, or I can ship it off to JLC or whoever and make this. It's going to be JLC because I'm trying to use their slightly monopolistic approach and make it for cheap, so that if I ever want to sell this, I can sell this for cheap. Okay, that's it for the stream. Bye.